Okay, hello everyone. So as Sabrina was saying, my name is Andrew and I'll be one of the chairs for today with Katrina.
Hi everyone, I'm Caterina Amendola. Nice to meet you here.
Awesome. So we'll get started with today's session. So this is the first Poster Blitz session. So again, just a few housekeeping points, as Sabrina was saying. Just a heads up for everyone, this session is being recorded and will be made available to the registrants for the conference. For the speakers, you each have 3 minutes. For the interest of time, we won't be taking any questions, but again, you can ask your questions on the fNIRS website. We will also include the link in the chat. So what you'd have to do is just click on the abstract of the speaker that you're interested in asking a question, and then you can post your question there. Just to know that you must be logged in to use the chat function. Okay, so without further ado, we'll get started with our first speaker for today. So our first speaker is Alexander Ruch from Carnegie Mellon University. And today, Alexander will be talking to us about measuring apnea progression and recovery in free divers through a self-calibrated SpO2 measurement. And you should now have access to the slides.
Yes, thank you so much. Yeah, my name is Alex, but I will be filling in for Jingyi Wu, who together with Jana Keinersdorfer at Carnegie Mellon is developing this self-calibrated pulse oximeter. So traditional pulse oximetry uses 2 different wavelengths, typically red and infrared. Looks like this thing in the top right. And if you take the modified Bartlett law for both of them and you solve it for SpO2, you get an equation like the one you see on the top. Sort of the input layer to this equation is this modulation factor, or the ratio of ratios, R. If you want to relate this to the actual oxygen saturation in arteries, you will need a calibration curve. And this calibration curve is typically only valid to about 80% of saturation, because that is a limit where you can expose humans safely to a low saturation before it becomes unethical. Everything beyond that is extrapolation. One major reason for which we need this calibration curve is the ratio of path lengths that is assumed constant. So we propose to use a method where we do not need a calibration. On the left side, what you see is sort of the solution if you were to solve for the ratio of path lengths using 2 different wavelengths, doing the same sort of calculation as seen before. The purple here is the input layer, so delta OD here is the difference between systolic and diastolic intensities. And then you have sort of an estimation layer, and that is the SpO2 over here. We compare this measured L ratio to an analytical L ratio. So this is the equation for path lengths in diffuse media. And the mu A here is also a function of SpO2. So now we have 2 different solutions, a measured and an analytical one. And the measured one actually has the sort of ground truth in it by measuring the delta OD. And so we try to set these equal and minimize the distance between the 2 by fitting or optimizing the SpO2 estimate. And if we test this in real life, so here we had divers in Italy diving down to 42 meters deep into a pool, and they would get a blood draw when they reach the bottom, and then they would come back to the surface after a 2-minute breath hold and get a second blood draw. And our analytical solution fits this invasive measurement of 60% SpO2 very well, whereas if you assume a constant path length factor, you can see that it overestimates this. So if you want to talk to me about this, feel free to find me online October 5th, 10 to 11 at Gathertown, or in person on the 10th.
Thank you very much, Alexander, also for being perfectly in time. Our next speaker is Weihao Fan from Washington University in St. Louis, and is presenting the abstract Investigating Effects of Modulation Frequency for High-Density Diffuse Optical Tomography in Neonates. So please, the floor is yours. you should be able to control the desktop.
Okay, thank you. So my name is Weihao Fan. I'm from Washington University in St. Louis in the Dr. Albrecht's lab. Today I'm talking about the effects of modulation frequency of the high-density diffuse optical tomography in neonates. So we use the frequency domain high-density diffuse optical tomography. So we use the multiple sinusoidal function modulated near-infrared spectroscopy on the human head. Looks like the figure here. The reason to use the frequency domain is because it can provide a better image quality than the continuous wave. And our previous work showed the optimized frequency is around 300 megahertz in the adult anatomies. However, due to the different geometry and the physiological characteristics in the neonatal head, we think the FDHD DOT could have a better performance in the infant head model. So in the FDHD DOT, the most important part is to model the light propagation in the human head, so that it's based on the diffusion equation, and the change of the optical density and the change of absorption in the brain tissue is related by a sensitivity matrix A. So here we simulate the light fall-off and phase shift in the head models in both adults and infants, and the sensitivity of the fixed source detector pair. And we can find that in the infant head, the light can cover more region of the brain. Then we simulate the brain point spread function in the infant brain to quantitatively evaluate the image quality. We focus on these 4 image quality metrics, which are localization error, full width at half maximum, and the success rate, and the field of view in the brain tissue. So our result shows by using modulation frequency, we can modestly improve the localization error and full width at half maximum, and the optimal frequency is around 300 megahertz. And for the field of view, on the top is for the whole head, the optimal is around 300 to 400 megahertz, and the bottom figures shows the field of view only in the brain tissue. The optimal is still around 300 megahertz. So we conclude that the optimal modulation frequency for the infants is about 300 to 400 megahertz, considering the localization accuracy, resolution, and the field of view. However, the effect of the modulation frequency in the infant on the image quality is less than that in the adults. So our next step, we will utilize more neonatal head models to generalize the result. And we think due to the smaller geometry and the relatively larger presence of the CSF, we may compare the current result with the Monte Carlo based modeling. Thank you.
Okay, thanks so much for the great talk. So we'll move on to our next speaker. So our next speaker is Quan-Chen Wu from Massachusetts General Hospital, and today he'll be talking to us about NIRS PPG to assess cerebral vasculature health. And you should have remote control access now.
Okay. Hi, everyone. Today I'm talking about our project on NIRS PPG to assess cerebral vascular health. So here we try to answer a question, can NIRS PPG pulse wave predict cognitive decline? Okay. Yeah. So as we know in traditional BPG, there are different features in the pulse waveform as such that indicate, give you some information on your cardiovascular state. As shown here, that there is like a shape difference between the younger and older population. And as previous research suggested that they can find a index that correlates well between the PPG waveform and the age as such. So we made a hypothesis that if we measure PPG on the head at longer separation, we might be able to find information about the cerebrovascular aging and predict the cognitive decline. So what we did is by using a fNIRS device that we made in our lab to measure it on a larger populations, including both the younger and older population on the forehead. So what we did is that first we removed the weird heartbeat and heart rates from the PPG we get, and then we do a cardiac gated averaging to the measurement we have, and then calculate the time derivatives and find the features within these pulse waveforms. So here we found that in the first derivative, if you look at the ratios between the first two peaks, you can find that there is a strong correlations between the older and younger generation as such. So in the older generation, we have the results of cognitive tests. First, we're just focusing on the old population here. And as we showed earlier, in the age, P1 and P2 correlates with the with age quite well, like such. And first, we look into MoCA, which is a measurement of cognitive impairment. And we found that the time of the first peak, and also if you normalize it, it correlates with this MoCA numbers quite well. And then we do a whole series of different cognitive tests, and then we found that as we show, the age correlates with P1 and P2. And then we also look at a dichrotic notch and found that the longer time to dichrotic notch correlates with self-reported executive dysfunction. And also the time to peak correlates with the worse cognitive abilities, as here indicates. So now we're getting more subjects, and we're thinking about doing some ANOVA analysis to see the effect of these different parameters. Thanks.
Okay, thank you very much, Quan Cheng, for your presentation. Our next speaker is AZA Alsop from Yale University, and he is presenting the abstract entitled Increased Neural Coupling and Ratings of Subjective Connection During Face-to-Face Gaze and Harmonious Music. So you should be able to control the screen.
Thank you. Everyone, my name is AZA. I'm a psychiatrist at Yale who studies social behavior, how it's represented across model systems, and how music, mindfulness, and psychedelics might alter those representations in social behavior. And we know really within my field that social connection is really critical for health, but a lot of the mechanisms that really facilitate social connection, either within a therapeutic context, or even within a community or family context, are not really that well known. We do know that music is well known to facilitate prosocial behavior across different cultures. And while there's certainly some social conditioning around how one has and develops musical preferences, there's also some universals across many different cultures. And so we wanted to look at one particular element of music, harmonic structure, and how that might be a way in which music might modulate social connection by looking at neural synchrony during face-to-face gaze. And so in our experiment, we have dyads, which both people can look at each other, and a transparent barrier that can either be opaque or transparent. And then we're going to play two different kinds of stimuli, harmonic stimuli or scramble stimuli. And so you end up with a 2x2 design here, as you can see, where you can have face harmony, face with scramble music, no face harmony, or no face with scramble music. So then we get these signals, we remove the global component and do a GLM. Having some issues with my slides, but after each run of that music, we ask them to rate how connected they feel to each other on a scale of 1 to 5, 1 being no connectedness, 5 being maximum connectedness. And so you can see here that when we look at their subjective ratings of connectedness, our hypothesis that it would be increased during harmony, and face was indeed validated here compared to the places where there was no face or even face and scrambled music. And if you look at the GLM, we see that certain areas like the angular gyrus, dorsolateral prefrontal cortex show significant activation when harmonious music is being played in comparison to scrambled music. Importantly, when we looked at coherence in certain areas of the brain like Broca's region and the LPFC, we saw increased coherence during harmony versus scrambled connections, scrambled conditions, which wasn't seen when we aligned those signals to partners that weren't actually paired. And so there seems to be some effect on harmonious music of not only modulating the subjective feeling of connectedness in the social network. So now we're going to look at gaze roles of these frontal regions, as well as social relationship in modulating these kinds of signals that we're beginning to see. You can look at more of the actual methodology details at our poster in person.
Okay, thanks so much for the talk. All right, so our next speaker is Hong Li from Beijing Normal University. And Hong will be talking to us about the high cognitive loads needs greater brain signal variability, a functional near-infrared spectroscopy study. Hong, you should have access now to these slides.
Okay. Hello. Hello, everyone. My name is Li Hong. I'm so glad to be here to share my work with you. My main research question is how brain signal variability responds to ever-changing task demands. Previous studies have shown that brain signal variability holds valuable information about brain dynamics rather than measurement-related noise. We cannot ignore it when studying the link between neuronal activity and condition. Okay, now let's see how do cognitive loads influence the brain signal variability. Only a little fMRI studies give us some answers. Garrett, using a face matching task, found that both SD changes in an inverted U-shaped curve as the task difficulty increases. In another MBAC study, he also found that for young adults and old adults, both SD appear to moderately increase with increasing task difficulty until the 2-bank condition, and either leveled off or tapered at 3-bank. Moreover, using adult lifespan sample, Boylan and Rick found that as working memory cognitive loads increase, young adults should decrease in both variability, whereas older adults should increase in both variability, but not significant. Besides, they found that modulation of brain signal variability across cognitive loads supported working memory performance, regardless of age. Although these studies suggest that brain signal variability is relevant to both task effects and behavior performance, the results were inconsistent. Therefore, we conducted a fNIRS study in 57-old adult sample. First, we explored the effect of varying M-bank loads on brain signal variability. Task PLS results showed greater SDHBO in 3-bank compared to 1 and 2-bank, mainly in DLPFC and sensory motor regions, which suggests that fNIRS signal variability can track working memory load. Second, we examined the relationship between brain signal variability and behavioral performance under different cognitive loads. The mean response time and response time variability were calculated as behavioral metrics. We can see that greater SDHBO in 2 and 3-bank was correlated with faster and more stable response time, which suggests demand-related up modulation of fNIRS variability serves as a hallmark of better cognitive performance. Thank you very much. Okay, that's all.
Thank you very much, Andy, for your great talk. So our next speaker is Jessica Gemignani from University of Padova, and she will talk us about the reproducibility of infant fNIRS studies a meta-analytic approach. So, Jessica, I think
Yes.
you have the control of the screen.
Yes, thank you. So, hello everyone. Yes, today I'm going to introduce you to this work. So, as you all know, concerns about the reproducibility of findings have emerged in several disciplines, from psychology to medicine to neuroscience, neuroimaging in particular. And there are several reasons for this replication crisis, from the undocumented diversification of data analysis techniques to the use of questionable reporting practices. And because of the challenges that come with developmental research, some of these issues can be actually aggravated in this field. To tackle the diversification, the undocumented diversification of methodologies, we all know that the community has been putting considerable efforts into establishing best practices that we can follow before, during, and after a single study is carried out to ensure its replicability. As for investigating the replicability of studies that have been already performed, meta-analysis are a useful tool as they allow to evaluate the robustness of a certain effect and investigate its moderators with a larger sample size. So the goal of this work was to exemplify the application of this tool to a series of fNIRS studies aimed at investigating repetition-based rule learning in young infants. To do so, we did a systematic search of the literature. The final sample included 23 studies on rule learning. The studies were carried out in 4 different labs, so different countries, machines, different native language of the participants. Stimuli included repetition-based strings, where at least 2 syllables were repeated, and diversity-based strings, which included no repetition. Then data analysis included reprocessing all the raw data and then calculating 2 types of effect sizes: an infant level effect, where the average brain response was compared to the inter-trial variability, and a study level effect size, where the average response was compared to the inter-subject variability. Then for the meta-analysis, we investigated the moderator's age, lab, and type of repetition, while we employed funnel plots and fail-safe number to evaluate the existence of a potential bias in the published literature. What we found was a strong effect of age when comparing brain responses to repetitions with the 0 baseline, with 6 months old, displaying a stronger activation in the left temporal area compared to newborns. As for the measures of estimate of bias, we found no asymmetry in any funnel plots, so for any of the comparisons. We also found that there would need to exist 126 negative missing studies, so studies in the drawer, let's say, to make the repetition effect not significant. So it's quite a large number that doesn't suggest the existence of a bias. In conclusion, the effect that we investigated is robust, replicates well across different labs and different experimental conditions, and we show that the meta-analysis is a valuable tool to identify relevant moderators, theoretically relevant. For example, in our case, we reveal a developmental trend that would not be revealed in any single study due to the sample size. If you want to chat and have more detail, I'll be in Gathertown today and on the 6th, and I will be in person on the 10th of October.
Thanks so much, Jessica. Thank you.
Yeah, you're welcome.
Okay.
We just wanted to remember you that if you have any question, you can go to the fNIRS website. We also sent the link on the chat. Okay.
Okay. So our next speaker is Kyle Tang from Western University. And Kyle will be talking to us about the altered functional connectivity patterns in term newborns with neonatal opioid withdrawal syndrome revealed by resting state functional near-infrared spectroscopy. Kyle, you should have access now.
Yeah, thank you, Andrew, for the kind introduction. So neonatal abstinence syndrome, or NAS, or sometimes also called neonatal opioid withdrawal syndrome, is a result of mother taking drugs off dependency during pregnancy, and then after birth, the drug is cut off and the baby shows withdrawal syndrome. And there is an increase of maternal opioid use during the last decade, so we could expect more and more babies need help for managing such conditions. Newborn with such condition have higher risk to develop into adverse neurodevelopmental outcomes, and this could be a result of disrupted brain function at an early age. And with fNIRS, we could access resting state functional connectivity and access the effects of opioid exposure on functional organization of brain in those babies. So in general, what we're trying to do is to see if there's any difference between opioid withdrawal babies and healthy controls in terms of resting state functional connectivity and brain functional organization. Okay, so because NAS baby is kind of a rare cohort for now, so we have only like 5 babies included in this study, and we have another 9 healthy babies as control. So fNIRS scan is done within 48 hours of their lives during resting state, and we are using NIRS system, and we have 8 sources and 8 detectors covering the whole brain, and that gives us like 20 channels in total. So we did a relatively standard pre-processing, and after that we extract a 6-minute scan from each of our subjects and calculate Pearson correlation coefficient to get the functional connectivity map. We filtered and binarized the connectivity maps to a certain level of sparsity, and we then use some graph theory-based matrices to analyze these maps. We use clustering coefficient and network efficiency as global measurements and some centrality-based metrics as local measurements for specific channels. So global analysis show that control group has higher clustering coefficient and network efficiency for both HBO and HPR networks. And potentially this indicates the overall disruption of functional organization, and local analysis shows the NAS group has lower centrality and the clustering coefficient around frontal lobe. This could mean that, the frontal lobe is specifically vulnerable to withdrawal syndrome. So in conclusion, NAS is associated with global and local functional connectivity change, and we show that using portable beta-side measurements in babies with NAS, we can identify some indicators of such syndrome at a very early age. And in the future, long-term outcomes are needed to determine the association of such alterations and developmental outcomes. So yeah, that's it. Thank you.
Thank you very much, Kyle, for your great presentation. So we can move on. And our next speaker is Harun Khan from Oslo Met University. And he's presenting the abstract cortical activation during signal length stance in alpine skier using fNIRS, a case study.
Thank you. Hi, everyone. I'm sorry for changing the title to a new one to convey a more direct message. Anyhow, we all know that maintaining a postural balance is an important part of our everybody activities. But when it comes to sports, it's more crucial, particularly for an alpine skier, where 1 second delay can greatly affect his or her performance. So there is a lot of literature about about balance from a biomechanics perspective, but we know very little about how the brain plays its part. The aim of our study was to investigate the contralateral hemodynamics changes in the brain during a single leg stance compared to a double leg stance. You can see in the figure 1 that one of the best alpine skier in Norway is performing a single leg stance on a challenging mat. We split the experiment into 2 parts. The first part is a barefooted walk, which is the most natural walking condition, and it gives us an idea of cortical activation during a simplest walking condition. Then we perform a right leg stance as shown in a figure 1A, and then a left leg stance as shown in a figure 1B. We consider dual leg stance as a baseline for our experiment. Yes, so we recorded the fNIRS signal using NIRS-2 with the 16 source and detectors over the motor cortex. We perform carefully the data processing steps due to a lot of motion artifacts in the data, and then we apply our GLM model. In the figure 3, we can see the fit of our GLM model to the OXY data. If I go quickly through the highlights of our results, so what we found is a barefooted walk has a comparatively less activation to a single leg stance. And the reason for that is that it is the most natural walking pattern with the barefoot, with a better foot position, biomechanics and balance control. We observed that frontal lobe was more activated in this condition, as we see in the figure 4 from A to C, which is very logical since the experiment took in a laboratory environment with a very limited space. So we can expect that. Single leg stance compared to a barefooted walk increase changes in HPO demands in a dorsolateral prefrontal and motor cortex area. The medial temporal gyrus was highly activated in both hemispheres during the single leg stance, which is really interesting for us to investigate further. When we compare the both legs during single leg stance, we found that the right hemisphere experienced higher HBO changes than the contralateral side. The reason for it might be that since the participant struggled with the balance on his left leg compared to the right one, which might enhance his oxygenation demand for it better postural stability all over the cortex from attention area to the motor control and sensory feedback. We see it in a figure from D to F. I will end here. This is a preliminary results of our study. We are recruiting more participants to get to know better. I hope to see you at the conference. If you have any question, we can meet there and discuss it further. Thank you.
Thanks so much, Arun, for the great talk. So we'll switch to our next speaker. Okay, so our next speaker is Ren Sato.
Yeah.
Ren will be talking to from Shibaro Institute of Technology, and Ren will be talking to us about the synchronization brain activity associated with eye contact, comparison of face-to-face and online communication. Ren, you should have access to the screen now.
Okay. Hello, everyone. I'm Ren Sato from the Shibaro Institute of Technology, Japan. I will introduce our study titled Synchronization of Brain Activity Associated with Eye Contact, Comparison of Face-to-Face and Online Communication. Sorry. Sorry,
Sorry, Ren, is it working now or?
Yeah.
Okay.
Sorry, slide is back, please. Okay, thank you. First of all, since the coronavirus pandemic started, web meetings have become common. Therefore, we aim to clarify whether there was any difference in the quality of communication between online and in-person meetings from the viewpoint of brain activity. So, in one study, brain activity was synchronized during eye contact. No study has compared brain synchronization in direct face-to-face condition and online communication through display conditions. Therefore, we did our study like this. 20 healthy students participated in this by using fNIRS devices, and there were two conditions, face-to-face condition and online conditions using Zoom. Thus, participants made eye contact with their partners in front of them or their partners on the screen. Specifically, they look alternately at their partner's eyes or less target. We measured 44 channels in the temporal lobe of the brain. In the analysis, we evaluated brain signal synchronization using a wavelet analysis. The figure shows the relationship between coherence and time. This red line is coherence of face-to-face conditions. The blue line is online coherence of online conditions. Therefore, we found that brain signal synchronization in the face-to-face conditions was higher than that in the online condition for several channels. Moreover, some areas were thought to be located at the temporal parietal junction, TPJ, and the inferior frontal gyrus, IFG. In conclusion, brain signal synchronization in the face-to-face condition was higher than that in the online condition. If you are interested in our study, please come and see our poster on site. Thank you for listening.
Okay, thank you very much, Jen, for your great presentation. And okay, so the next speaker is Hailey Hudson from Boys Town National Research Hospital, and he's presenting the abstract titled "Sex Differences in Neural Profiles of Toddlers at Risk for Attention Deficit Hyperactivity Disorder." So maybe now, Hailey, you should be able to control the screen.
Okay, thank you. My name is Hailey Hudson, and I work at Boys Town National Research Hospital. I'm studying sex differences in neural profiles of toddlers at risk for ADHD. So ADHD is a neurodevelopmental disorder that affects 7 to 11% of US children, and the goal of this study was to specifically target areas of the ADHD phenotype that are currently lacking in research. First, we wanted to see if we could develop a neural profile for children at risk for ADHD to possibly help with earlier diagnoses, as this could help children's prognosis in school. And we also targeted sex differences and symptom profiles to understand the broader ADHD phenotype. Here you can see the methods that we used in a breakdown of our demographics. We used a passive viewing paradigm to measure resting state functional connectivity using the NIRS-SPORT2 model. And then this graph shows that the strengths and difficulties questionnaire total difficulty score, which we used as our symptom profile measure, was significantly higher in our risk groups than the typically developing groups, which would be expected if they were to be diagnosed with ADHD in the future. So looking at our resting state neural results, all controlling for age, we did see neural differences in functional connectivity between risk group and between the male and female children, as well as an interaction with the increasing total difficulty score on the SDQ. Generally, children at risk show global hypoconnectivity compared to TD children in both male and female children, and generally male children showed less refined and pruned connectivity than the female children in both groups. You can also see differences in the cross-hemisphere connectivity in that TD children and female children show connectivity between the prefrontal cortices, which is not present in the other groups. And the direction of the connectivity between the parietal and the prefrontal cortices changes between groups as well. Secondly, we saw that male children showed more connectivity between the parietal cortices, and then in the risk group, there was no cross-hemisphere connectivity seen at all. And then we also saw that with the SDQ total difficulty score, as the score increased, there was a lot of disorganization in the functional connectivity globally. However, this result was much more pronounced in the male children than in the female children. Overall, we concluded that there are distinct neural differences in this age group, both based on sex and having familial risk of ADHD. The sex difference that we saw specifically seemed to align with the global maturational delay hypothesis, and this could be a factor of why more male children are being diagnosed with ADHD than female children. We plan to continue and follow up with these children to see if familial risk is predicting ADHD diagnoses, as well as compare these results to a clinical ADHD population of older children to see if these results are predictive of neural profiles of children with a diagnosis of ADHD. And then we also want to see if there are sex-based differences interacting with the subtype of ADHD to extend our work with symptom profiles to clinical practice. Thank you so much for listening, and I hope you come stop by my poster.
Thanks so much, Hailey, for this great talk. Okay, so our next speaker is Mindy Chu from Yasuya Minagawa, Mindy Chu from Keio University. And Mindy will be talking to us about 2-in-1 system and behavior-specific brain synchrony during cooperative goal-free creation. Mindy, you should have access to the screen now.
Okay. Thank you for introduction. Hello, everyone. I'm Mindy Xu. Today, I would like to introduce our hyperscanning study from Keio University, Japan. Sorry, can't go to the next. Okay. We designed a creative interior design game. 39 devs participated in 2 cooperation game and 2 independent game. During the cooperation game, they were instructed to design a room that not only satisfies themselves, but also the partner. And there is no constraints on communication or time. And during the independent game, they were instructed to design the room on their own. Their brain activity in the right hemisphere were simultaneously recorded using 20 channels respectively. First, the brain activity synchrony between 2 brains or within 1 brain were estimated using conventional wavelet transformed coherence analysis. Many behaviors may have contributed to the stronger synchrony. So here we focused on one type of specific social behavior, face up. That is when participants raised their head from their touch panel. A MATLAB-based computer vision method, OpenFace, was used to automatically extract these face-up epochs. You can see that these bars indicate the epochs when both participant A and participant B raised their heads, and these single bars indicate the epochs when only one party raised their head. And we used these events as regressors of GRM to isolate brain synchrony that was correlated with such events. We can see that brain regions that showed significantly stronger within brain synchrony, that is connectivity, during independent play. The regions are from MTG and SDG, and also frontal polar and the DRPFC. They worked together in the cooperative session, functioning like a 2-in-1 system. We can also see that, importantly, during a cooperative game, although the connectivity within one brain is very limited, but the brain activity was connected to the activity of another brain during the cooperative condition, indicated that, is the time limit. So probably because participants allocated more resources to attend to partners to adjust oneself accordingly. GRM analysis uncovered that between brain synchrony of right DRPFC and right TPG was significantly correlated with either up events. Considering the functional roles of these regions, this synchrony indicates that more effort is necessary when facial information exchange is limited to only one direction. Our poster will be presented on October the 5th at GatherTown. Please come and welcome for further discussions. Thank you very much.
Thank you, Mindy. And we can move on to the next speaker. Our next speaker is Alejandra Rocha Solange. Sorry if I'm not pronouncing it in the correct way. From the Instituto Nacional de Astrofísica, Óptica y Electrónica. And the abstract title is The Space-Time of Effective Neural Connectivity for fNIRS. So, Alejandra, the floor is yours. You should be able to control the screen.
Okay, thanks, Katerina.
Thank you.
And hello, everyone. I'm happy to be here in this first Poster Blitz. I am Alex Rocha, a master's student in computational science from the National Institute for Astrophysics, Optics, and Electronics in Mexico. And I'm going to present the advances that our research has made in terms of the space-time connectivity for fNIRS. We're interested in studying the nature of effective connectivity, and as is well known, is a phenomenon that seems to be a good candidate for modeling as causal problem. To be more specific, when we talk about causality in mathematics, we can find several definitions that have been established to express cause-effect intuitions. In this work, we're interested in providing that effective connectivity can be studied in terms of single causality. And to gain intuition, this type of causality is defined at level of sets and is present and supports the causal geometry of space-times in the special relativity theory in physics. We hypothesize that there is a well-defined topological manifold that is able to contain information associated with effective neural connectivity recorded in fNIRS observation. Okay. Yes. Okay, in previous work, we have proposed that four-dimensional space-times that have the shape of a Lorentzian hypercubinder or cubinder. The dimension of this space encodes the phase, frequency, and time. And then the fNIRS series are projected as events or points of this space via short-time Fourier transform. We keep this space with a distance function that allows to identify if two events are reachable in time, which will imply a candidate of causal relationship, and also allows to discard those events in which the spatial separation makes it impossible for these events to interact. But in order to ensure that our space-time is able to express causality, in this paper we present analytical evidence that the cubinder satisfies the causal ladder, a hierarchy of topological conditions. Each one expresses a causal property that is stronger than the previous one, and that allows to ensure the non-existence of space-time inconsistencies, such as time loops, and thus our intuition of cause effects is correctly preserved. We conclude that our space-time is strongly causal, and in addition, we present experimental evidence that we'll be happy to discuss our poster stand on the webpage of the Congress. Thanks.
Hey, thank you so much, Alejandra. All right. So we'll move on to our final speaker for the day. So our final speaker is Megumi Kobayashi from Niigata University. And Megumi will be talking to us about development of cortical processing of dynamic bodies in infancy. You should have access now to the slides.
Thank you for the kind introduction. Today, I'm going to introduce our recent findings that the bilateral superior temporal regions of infant brains process dynamic body information at rates from 5 months. Previous studies have shown that the bilateral temporal areas activate for static and dynamic phases, but little is known about the development of cortical processing of bodies, especially for the dynamic bodies. To examine this point, we used an fNIRS techniques, and we conducted 3 experiments. In the experiment 1 and 2, we directly compared to cortical activation in response to dynamic bodies and phases. And experiment 3, we measured the cortical activation related to the configured processing of bodies by assessing the body invasion effect. We used the videos of approaching people blurring the faces of bodies. And we calculated the scores of active hemoglobin concentration in each channel during the 2 tests conditions against the active hemoglobin responses during the last 2 seconds in the baseline. Here is the result for the experiment 1. The top line graphs represent the time courses of the active hemoglobin concentration during the presentation, the face-only condition, which is the blue line, and the body-only conditions, which is the orange line. The bottom images represent the channel that shows the significant increases of oxyhemoglobin concentration compared to the baseline. As shown here, the superior area of the bilateral temporal region significantly activated in response to dynamic bodies and faces. And cortical responses to dynamic bodies did not change across ages. But for the faces, the more channels activated in the older infants than in the younger infants. And in the experiment 2, we confirmed that when the body-only, the face-only stimuli were inverted, there was no significant activation in both age groups. So the last experiment, we compared the oxyhemoglobin concentration in response to upright body embodied bodies. As shown here, the superior areas of bilateral temporal region show the body inventory effect. So I would appreciate if you give us some comments in person, post the presentation on next Monday or on the website. Thank you.
Hey, thank you so much. So actually, that concludes today's session. Thank you, speakers, again for joining us to this first Poster Blitz session. And just a reminder, there is a gather down meet happening afterwards if you want to check out some of the posters. And we also invite everyone to join us tomorrow for the virtual posters in the spotlight session as well. That's happening again at 8 a.m. Eastern time. So with that, again, thanks everyone, and we hope to see you tomorrow.
Thanks everyone, bye.